So I just looked at who has looked at the answer keys to the last exam, because I would encourage you to go over it so you could have read my explanations and seen what the right answers were, because a lot of you seem to have questions. Well, that's why I write answer keys, so that you have an explanation from me for all of them. Only 4 people in the entire class out of 62 have even looked. So instead of me sitting here telling you what I've already written down for you, which was available right after the exam too, look at those first. That's why I wrote them. I'm happy to explain things to you, but I don't need to be redundant. For those that have looked at it, they don't want to sit here listening to me say it again. So I thought more people were going to look and we would do it. But is there anything that's killing you though right now? You do want to ask, but my point is I have tried to give you an explanation for them if you're confused. So at least look at what I said first. If that still doesn't make sense, by all means, I'll be happy to explain further. But anything that's bothering people right now, just can't wait. Do you?
No, I'm looking at the...
You sure?
Right now, yeah.
Oh, you're looking at... Well, through class. Raise your hand if you've looked at the one that was bothering you. Anybody else? All right, any questions about anything in general?
I have too many.
Yeah, Eddie?
Yeah, just going to Newton's third law.
Newton's third law?
Yeah. I understand all forces come in pairs.
All forces come in pairs, equal and opposite.
There was a question that kind of on the exam that brought this. It's not specifically about the exam, but one that kind of brought it up. So is that only applicable when it's not in equilibrium? I mean, meaning...
It's always applicable.
Because if I'm pushing, like if I start pushing on a box on the ground, it's going to oppose me equally until I overcome the friction, right? Friction force. But then won't my net force, isn't it a net force that's accelerating that mass? So therefore...
Let's look at that one.
Equal each other? Does that make sense?
So if I push on this, it pushes back with an equal and opposite force. But at some point, it starts to move. The force I exert on it overcomes the friction trying to push it back. Friction's not the reaction pair.
Okay.
Friction's acting on this, trying to make it move. I'm acting on this, trying to make it move. So those can't be, because they're on the same body. The action-reaction pair is me pushing on it, it pushes on me. And that force is the same.
Okay, that's right.
It pushes on the table, and the table pushes on it. That force is the same. And those actually are equal until it starts to move. When my force exceeds the frictional force on it, then the forces aren't balanced anymore. There is a net force that's not zero. I'm winning. And it'll start to move. But now let's look at that. I'm still exerting a force on it, and it's still pushing back on me with an equal and opposite force.
Force pairs are still equal.
Yeah. Even in collisions, things hit. But let's say this one can't handle the force, and this one can, so, it starts to move, or it crumbles or breaks. Well, the force between them is still the same. The force of my right hand on my left hand is the same as the force of my left hand on my right hand. And for momentum and impulse, while they're in that interaction and touching each other, they're in contact for the same amount of time. So the force is the same, and the time is the same, so the impulse is the same during the collision.
It was the acting on the same body.
Yeah, that's the biggest thing with Newton's third law for almost most people is that whole, which one's the action-reaction pair? Yeah, and my biggest tip-off is they have to be on opposite bodies. So if they're on the same body, you can nix it right there. I always talk it through. Like the most confusing one is, okay, my weight, and I'm trying to lose it, but 180 pounds down. That means the earth is pulling on me with 180 pounds. See, I've often done it that way. The earth is pulling on me. That helps me with the pair. That means I'm pulling on the earth. The pair isn't the floor pushing on me. See how the floor pushes on me and the earth pulls on me? That's both on me, so that can't be it. Anything else at the moment? Yeah.
One quick question about number
30?
30. I guess it's more a question about interpreting word problems. Because when I read through it, I kind of needed to say, so you're looking at your watch.
Can you read it? Because that must have been when my printer ran out of paper and I don't have the last two questions.
Oh, right. So compared to standard Earth time, there's a physical slowing of your time.
Oh, that one.
When you travel at relativistic speed.
Okay.
And so I put relativistic speeds.
Yeah. Which was the most common missed choice.
Yeah.
So compared to standard Earth time, you're looking at your watch, tick, 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 tick. You got a clock on the wall, tick, tick, tick. It passes by, and it doesn't seem to change for people, no matter what we do. And it's obvious. If we take off on a spaceship, whoosh, there's a physical slowing of our time compared to that time. You agree with that? Well, anytime there's relative motion between two reference frames at all, there's time dilation. So even me moving around like this, technically, my time is physically ticking more slowly compared with that time. Now it's imperceptible at such a slow speed, but it is there. And so the theory of relativity, as I mentioned, applies at all speeds. As long as there's relative motion between two reference frames, it's just at our normal everyday slow speeds, we don't have to worry about it because it's such a small effect. As you go 10%, 50%, the speed of light, it becomes conspicuous and you have to account for it or you'll get things wrong. Does that help?
Yeah. And so, well, my main question is when I was talking with a couple of people that know physics more than I do, they were saying it was none of these because they said they thought it was like, oh, you're looking at your own watch. Like, does that make sense? If you're looking at your own watch.
Oh, so misinterpreting the question to think your time meaning with respect to you.
Yeah.
Yeah.
So I guess how would we interpret that?
I think it said compared to Earth time.
Okay.
But good point. I mean, I won't lie. I struggle over writing questions or adjusting them, the authors, if they're there. If I ask that again, I can word it clearer.
Well, no, I was just like...
No, because I mean...
What's the good way to... That's one thing I've always struggled with. Like, if there's just a number problem, I can get it. But as far as
Their words.
Word problem, I always...
Well, I'm happy for suggestions. I tweak them all the time. If during the exam you're confused whether I mean that or not, certainly ask me. The sad part is where you thought I meant this, and so you don't even question it, and that's how you answer. But then tell me afterwards. I've been known to change scores because if you can justify it to me, that's how you interpret it. I see that it's valid, and based on your thought process, that would be the correct answer. Well, sure. Sure. Thanks for bringing that one up. I think somebody else did too. Was it Ryan? Is Ryan here? Yeah. How you feel about that one now?
Yeah.
A little better? He had the same question. Others? Okay. I made a list of some densities for reference. Density is mass over volume. So the standard units are kilograms for mass and cubic meters. Picture a meter on all sides, big cube. Then here's the densities for various things. Air is about 1.2. Helium is a lot less. Excuse me. He is helium. That's one reason why helium balloons float, yes. And that's where we're headed today in this lecture. Sinking and floating. Water is 1,000 kilograms per cubic meter. You can see ice is a little smaller. Remember, water expands when it freezes. So for the same amount of it, if you took the same mass and froze it, it would expand and take up a little more space. So it has a smaller density. If you add salt to water, you're putting more mass in the same space. It fills in the holes amongst the molecules in water. And you get a slightly greater density for seawater. And that's its value. We also had The relationship between pressure, force, and area. For the same, if you take a certain force and change the area it's exerting over, you can increase the pressure or decrease the pressure. Likewise, if you rearrange that, you can take something with a certain pressure, and if it's acting over a large enough area, you can get a big force out. If you take a pressure and exert it over a small area, you get little force. Or it requires little force to have that pressure. Make it a big area, you get a lot more force. This is the principle behind hydraulic presses, Megan. I responded to you. I don't know if that helped, but I don't know if you read it yet. A hydraulic press is like a simple machine. Let's say you got a fluid in here, and this works because of Pascal's principle. Blaise Pascal, the guy that figured out this relationship and helped us understand it. It states in your book that a change in pressure at any point in an enclosed fluid, so like this, see how this fluid's enclosed? Let's say it's full of water. It's enclosed. If you change the pressure at any point in there, then that's transmitted equally everywhere else. Again, that's defined in your book. That's Pascal's principle. It just means if you push over here, it's going to exert pressure there, right? A force over an area, force over an area. So you're exerting a certain pressure here. That's transmitted equally in this enclosed fluid that's at rest over to here. Do you see how this area is bigger? What will happen with the force over there? It will be greater. If this exerts a certain pressure, and the pressure is equally transmitted, P, then if you have the same pressure over here, but over a bigger area, you can get a bigger force out. This is how one way you can lift up cars. You know, when you drive over, you can exert a little force over here and lift up a car over here, something that weighs a lot more. Does that make sense? Yes?
This might be kind of off topic, but could you kind of explain how like hydraulic shocks work? Is that only if it like ties into the topic?
Hydraulic shocks?
Yeah, or like, so like for mountain biking and stuff like that, like I can make pretty much design like all the parts of the mountain bike, but like when it comes to the shocks, like I have a hard time understanding like the air shocks. They have some with fluid inside of them. I think.
Well, I won't.
I understand it with the spring, but I mean only if it really ties in. I don't really want to like.
Well, no, it does. I'm more thinking I'm not as familiar with hydraulic and air shocks as much, so I'm processing in my head, thinking well how that could be working out. What I'm assuming is you exert a pressure. I don't know. There's something in here, a spring or a fluid, and there's probably a piston. You know, and here's the load, you on the bike, and one way this happens is you're exerting a force that's over an area, so there is a pressure there. It's equally transmitted, because of Pascal's principle, throughout this fluid, if it's a fluid, air or water. Water would work better, a fluid. There's also a dampening effect, like if you're trying to move through air versus move through water, it slows you down. So I know that's part of it. Thing is here, I don't understand if there's more connected. If it's just this, you're trying to compress the fluid, but it has nowhere to go. That's going to increase the pressure in here. So maybe you could have, if it starts here, versus if you like tweak something, it could be here. Thus, for the same jarring and load force, it would have more pressure pushing back against you. Whereas you can picture if this was all the way out, whoosh, you would move a lot more with that before it could stop you, because it would take longer to compress. And I can totally buy that. I wish I understood it more. But it is because of changes in pressure. And ultimately, it's over a certain area. And you got a force coming in, and the pressure over that area is a force coming back. If you can balance them, it'll stop you. If you can have more force here by changing the pressure or the area, you can stop bigger loads or stop smaller loads quicker. Do you have a question, Candelaria?
Yeah, I have a question about what you were saying before. This is, you are trying to explain the hydraulic pressure.
Hydraulic press.
This side is wider and the other side is narrow.
Yeah, basically if you change the area. See, this is a bigger area, smaller area.
What is what you draw on top of that? What means that?
This?
No, the little frames involved.
Oh, it's closed off. Think of it as a platform. Let's think of this as air, this is water, and this is a plug, like a piston that can move up and down. It seals it so the water is enclosed. And you can picture yourself over here just pushing down on it. If you exert a force on it, that force is spread over this area and it creates this pressure. Pascal's principle says that pressure is equally transmitted throughout an enclosed fluid at rest. Thus, we end up with the same pressure over here. It's the same pressure.
And also that square is also closed.
Yes, it's another plug piston thingy. Because if the water can squirt out, it will, and you've kind of defeated the purpose. Now, this isn't a simple machine, but remember our simple machines? What do they not multiply? Work. Energy is conserved. You can't, you're going to put in the same amount of work on one side as you do on the other. But they can multiply what? Force. The simple machines could make our lives easier. Remember, say you can't lift that refrigerator into the truck straight up because it's too much force. I can't lift it. But if you go on a ramp, I can push it up a ramp. That doesn't take as much force. But what has to give? I have to push it for a lot longer distance. Do you remember that work is force over a distance? So it was this idea. If you have the same work on both sides, you can do a little force. So now maybe it's possible for us, like the ramp. We just do it for longer, as opposed to a big force that I just physically can't do over a little distance, straight up, about 2 feet. Hydraulic presses work the same way. Which side would move further? Physically, these pistons will move up and down. Which side would move further? This one? Right, this requires less force. So you'll have to displace this side more. Let's put some numbers to this. And I'm starting to get messy over here. Let me redraw it. Let's say I push a force of 100 newtons over here, and I can get, forget that. Let's do, and this area is, 1 square meter. Let's say this area is 10 square meters. You tell me, how much force can I get out over here? That's right. Your gut's right. 10 times. If the area is different by 10, then the force has to differ by 10 to keep the pressure the same. So 100 over here times 10, you can get a force of 1,000 newtons over here. You with me? And let's say I have to push this, or I can push it a distance of, I don't know, 5 meters, which is a lot, but I'm making this up. So how far, oh, let's make life easier so we don't have to think as much. 10 meters. If this one I displace 10 meters, how far will this one go up? 1 meter. A factor of 10 again. This one would go up 1 meter. Now look. F1, D1, F2, D2. Let's see how much energy we exerted over here. 100 newtons for 10 meters. 1,000 joules of energy exerted on the right-hand side. Force times distance. Over here, we exerted 1,000 newtons, but for only 1 meter. Do you see it's the same? Energy is still conserved. You can't multiply energy with simple machines or a hydraulic press. Energy is conserved. But you can multiply force and make your life easier by messing with this ratio of force and area. That's what this little thing was for those of you watching my friends play with it before class. It's a hovercraft. So it's just 2 boards and they sandwich some fabric. The air is going to come out of these holes. And you blow air in the front here. So, you know, I can't do this one by myself. I need a volunteer. All right. Now, this exerts a certain pressure. But it's not much pressure. I can stop it with my hand. And this will not lift her up by itself. But if we have her sit in the middle, yeah, we'll have you scooch this way a little for center of mass. We'll shove it in here. Here's the switch. You can hold on to that. We're going to have her turn the air on and take that pressure, but shoot it out the bottom underneath. And it's going to spread it over this whole area. So if we take the same pressure and multiply it over a big area, we can increase the force. So go for it. It just goes, yeah. Okay. Thanks.
Where did you get that? Did you make that?
This one is commercial, but I've made more than I've bought. It's 2 pieces of wood, here and here, and we just sandwiched them together. I usually get a tarp, like at Home Depot, attach it in the middle, get some holes. I mean, that's all there is to it. If she sits in the middle so you don't tip, and you spread that pressure over all this area, you can have more than enough force to lift her weight.
So how does the air
Comes out of these holes. Yeah, so there's a hole here, obviously.
So the fabric's not porous, it's all coming out of this.
Yes, it's all coming out of here. There's just a hole in this piece of wood. Actually, this one actually isn't 2 pieces of wood. It's lighter that way. But there are 2 here to clamp the fabric together so you have a place. You could just bring it over the top and staple or duct tape the heck out of it, right? You would need to seal it so the air doesn't leak out there. So then all this air would come in through the wood into this, and the only way out is these holes.
So would it be more effective if you took the holes, took them out,
If you made the holes bigger?
Not the holes bigger, but say
Had them further out here?
Yeah, would that be more effective? Because it's a bigger area.
That's a good science fair project. I don't know. I've seen them out here. It's kind of a balance between if you have too many holes or too big, then all the air leaks out too fast. But so you don't want too many or too big. But then it's just playing around with it.
And if I make the same, in the same place, a smaller hole.
That'll work. Since you guys are into this, I'll tell you a story. But this is a hydraulic press, right? It's essentially, I'm putting pressure on one side over this area. Spread it over the same pressure over a bigger area. I multiplied the force. It was a hydraulic press, in a sense. So I bought two, it was at Colorado State University. I'll give the Little Shop of Physics, an outreach program I worked with, credit. But we took two tarps, from the edge of the table to, I don't know, here-ish, and we duct taped the heck out of it around. So it was a big pillow. And we put two leaf blowers. It works with one, but two's faster. In the corners, just a little enough hole to put them in there, hold the bag around it so the air couldn't leak. Filled the bag up. And it would inflate itself like this tall. We could get a whole elementary school class on top of it. They would be sitting on the bag on the floor, and we'd air it up, and it would just lift the whole class. Some of them would fall off, but they liked that. You get a big enough area, the force just keeps going up and up and up. We're not multiplying energy. The energy came from this, which ultimately came from electrical energy. And we're still getting the same amount of work out on them. We're just changing the force with the distance. I didn't raise them very high, and it took a long time, but it worked. Groovy. So there's hydraulic press. Now we're actually going to go back in the chapter slightly and show you something. All right, for those of you that don't like math, forgive me now, but I think this is cool. Okay, we got pressure is force over area. Force. Let's talk about our weight. If that's our weight, you know that. It's mg over area. That's not a big stretch. You guys know that. You know all these steps. But now, since we're dealing with fluids, instead of dealing with just mass, sometimes volume is more useful. So I'm going to use that relationship of density as mass over volume. If we rewrite that in terms of mass, you can think of mass as density times volume. I'm going to plug that in for the mass up above. So I'm going to put this right there. You with me? Now, remember your geometry? You got a cylinder. And what's its volume? It's the area of one of the ends multiplied by the height. Volume of that cylinder would be the area of one of the ends, whatever its shape, times the height. So I'm going to put that in up here. Density, area times height, gravity, over the area. Because now you can see the areas go away. They cancel each other, and you're left with and DGH. This is our new guide to thinking. Combining this density and Pascal's principle, we can think of pressure as the density of the fluid involved times gravity, because remember it's about this weight that's providing a pressure, for however much is on top of you. Remember we talked about however much air is above us? So if we take the density of air, 1.2 kilograms per cubic meter, 10 meters per second, and the height of the atmosphere above us, then you got atmospheric pressure. You get the same values. If you dive down in water, you take the density of water, 1,000 kilograms per cubic meter. Times gravity, because gravity's still acting on that water. And let's say you're 10 meters down. Let's figure that one out. If you're 10 meters underneath the water, what's the pressure on you? Let's see. Density is 1,000 kilograms per cubic meter. Gravity, we'll just round to 10, like we've always been. And we're 10 meters down. You get, since we used all standard units, it comes out to pressure standard unit, which is a Pascal. 100,000 pascals. If you remember from last class, that's about 1 atmosphere. So all of the air on top of you right now that's exerting pressure on you is equivalent. You can create the same pressure by just putting 10 meters of water on top of you. Or if you go down 10 meters, you got 1 more atmosphere on you. We sort of discussed that with diving last time. So, pressure is depth dependent. Dependent. Depth dependent. It doesn't care how much is spread out on top of you. It matters how deep you are. Let's do a few to show you that. Here's one. I'm going to pour some water in this vase. And there's a valve down here. I'm going to release it and let it push water into these. So right now, this has this much water on top of it. So we could figure out the pressure. We know the density of water, we know gravity, and we know how high up it is. So right here, there's a certain pressure. When I release this valve, that pressure is going to cause the water to squirt into here. It's sealed here, but it's open to these. Water will come up these. But how high will it go? Which one will fill up taller? You say they'll be equal? This one? Exciting. Ta-da! They're all equal. Very good. Can you see that okay? That one's a little thin to see. Can you see that? The point I'm trying to emphasize with this is pressure is depth dependent, not volume. A lot of people think, oh, this one's going to be the highest because it's got the most water in it. But it doesn't matter how much water this way you have. It matters this, what's on top of you. This one exerted a certain pressure here. That was the same pressure that went over here. So you have the same pressure here, here, and here. It pushed them up the same height. Even though this one goes, and this one gets thinner, there's a whole lot less water here than here. Practical application, dams. You can have a big dam holding back some water. Right? Get all this water. The pressure at the bottom of the dam, right here, is much greater than the pressure here. Isn't it? You got more stuff on top of you. I'll come back to this, but let me show that. Here's a cylinder, and I got 3 plugs. The top, the middle, and the bottom. I'm going to unplug them. Water will shoot out because there's a certain pressure here, here, and here. Which one do you think will shoot out further? You're right. Shoots out faster and goes further. You can see as the water level comes down, the pressure decreases here. You can see it shooting out less. But there's still more pressure down here. It's decreasing also. And see, when the water level gets there, there's not enough pressure to shoot it out. Good thing I went to the bathroom before this class. All right, you get the idea. So yeah, the deeper you go, the greater the pressure. Yeah. Yeah, this is very good observation. This is mostly for fluids that are at rest. At the end of chapter 14, we're going to take fluids and start moving them. And that can cause pressure differences also. Fluids that are in motion cause changes in pressure. So right now, yeah, not moving. So back to the dam example. Since the pressure is greater here, nobody builds a dam like I've drawn it. It would bust here. They usually look like this. They get thicker at the bottom in order to withstand that big pressure. And a little pressure. But also, let's say this lake is, 1,000 meters deep. Would you need a bigger dam, a smaller dam, or the same dam to hold back the entire ocean if the water level at the dam was 1,000 meters deep? I'm sure there's a spot on the coast somewhere where the depth is 1,000 meters. If you built a dam there to hold back the whole ocean, would that dam need to be bigger, smaller, or it doesn't matter? Very good. It doesn't matter. It doesn't matter that there's that much of it. It's still 1,000 meters down. It's the stuff on top of it. This little section. That's what creates the pressure. This fluid density, acted on by gravity for that depth, creates that pressure there. It doesn't matter if you have this much of it, or this much of it, or this much of it. It's still the same pressure at these points because it's the same depth. This one lowered, but they all ended up equal. Because down here they're connected, and the pressure's the same. All right, Archimedes Principle. I like this principle. Archimedes it's definitely a wet lecture. All right. Archimedes Principle, I'll show you through this. So here's a spring scale. It measures force. These two, what are their weights? They are, let's call it 7 newtons. Can you see that okay? I'm going to fill up this container with water, but there's a hose attached, and so the water overflows. All right, so this is filled up to the brim essentially. Any more water and it flows out. Empty this. We'll start with this one empty. All right, one question. I'm going to raise up this reservoir so that this is submerged. What do you think will happen to the force on the spring scale? Will it stay the same? Because this will be in water? Will it go up? Because I'm putting, somehow I'm bringing water to it, and it has to weigh that too? Or maybe it'll go down because the thing's kind of floating. I don't know. Up and then down. All right, that's what this demo is for then. Help you figure out that answer. These are balanced. See, they can go back and forth. So they're mostly balanced. Got the same amount of water over here as I do over here. What do you think will happen if I put the ball on this side and drop it? It'll go down? You're right. Now this has to hold up the weight of the ball and the water. Okay. What if the ball is attached? Like my finger. I'm just going to take my finger and push it into the water. Let that settle. You know what happens when you push things into water? I'm just going to do this. So I'm still holding my finger up, but it's in the water. It just pushes the water aside. What will happen now if I just push my finger in this side? Nothing? It goes down. Why? Buoyant force. What is a buoyant force? How would you define it, Eddie? I haven't defined it for you yet. I mean, most people have heard of a buoyant force, buoyancy, but what is it?
Displacing water.
Yeah, I'm displacing water. This displaces water. This displaces water. And what was that?
The water pushing back on you.
Hey, see Newton's third law. If I'm pushing the water to push it aside, the reaction is the water pushes back on my finger. That's kind of where the buoyant force comes from, or one way to look at it. You know this because when you're in the swimming pool, don't you feel like you're lighter? You're floating. You haven't changed your mass. Gravity's still pulling down on you, but now you have the water buoying you up, pushing up on you, so you feel lighter. That's what's going on here. I push down on the water, it pushes back up on me. Now another reaction pair. If the water's pushing up on me, what's it pushing? Where does it get its leverage? It's pushing the scale down. So that's going to happen over here. I lift this up. This is going to displace water, and it's going to move it to the side. This is going to push on the water. Some of it should overflow. What's the water do to it? Watch the scale. What are we at? 7-ish? If I can do this without spilling. So it's displacing water. There we go. Whoop. And I'm trying to get it submerged, but it's not touching the bottom. So see, it still swings. So that's completely under the water, but it's not touching the bottom. It displaced this much water, which, by the way, is the exact volume of the object. What happened to the force? Oh, it went down. Let's call it 5.5. So it went from 7 to 5.5. So 1.5 newtons. This weighs 1.5 newtons less. What's the buoyant force? 1.5 newtons. One way to think of buoyant force is the difference in air, the weight in air versus the weight in water. If all of this was 7 newtons to begin with and now it's 5.5, then there's now a buoyant force supporting this cylinder with 1.5 newtons of force. So the scale doesn't need to hold up with that. Now, take this water. I can pour it into this, which I failed to do at the beginning. So one more step after this. This is hollow. There we go. All the water fills that up, and look where it went back to. That's Archimedes' principle. The weight of the displaced fluid. This is in your book. The weight of the displaced fluid is the buoyant force. See how it went right back up 1.5 newtons? This water weighed 1.5 newtons. I just put it back in. This is the exact water that was displaced by that object. Archimedes' principle, again, is buoyant force is equal to the weight of the displaced fluid. It doesn't care how heavy the object is. Did you catch that? That'll help you with a lot of these problems. It doesn't care the object of the weight of the object. It cares the weight of the displaced fluid. It doesn't matter how much fluid's underneath it, just how much it displaced. Let me show you also, if I take this off carefully, and this one off. This fits in here, and it's the exact same volume. If you completely submerge an object underwater, it displaces a volume of water exactly equal to its volume. If it's only half submerged underwater, it would displace half its volume. Whatever's underneath, it displaces that volume. But again, that's Archimedes' principle. The weight of the displaced fluid is the buoyant force. And that'll be the difference in your weight in air versus what you weigh in water. It's because that buoyant force is helping lift it up. We got 2 minutes. I can do it, because this will help you. Not your clickers. This is just an animation. And I'll end with it. It's just saying the same thing. All right, so here's a cylinder of water, and here's an object floating. These blue arrows represent the force due to the pressure. If I go farther underwater, whoops, depth underwater, see how the force increases? Because the pressure increases. We did that. Pressure is depth dependent. Now let's make the object bigger. You can see the arrows, the magnitude is bigger down here than it is up there. It's another way to look at buoyant force. And if we make it a little farther down, how about right here? The pressure here you're not as far underwater, so the pressure's less. Here you're farther underwater, so the pressure's more. Notice there's a difference. There's a net force. That's the buoyant force. It's because pressure is depth dependent that you get a difference on the top versus the bottom. That provides the buoyant force that is pushing up on you as it displaces this fluid. So there's a few ways to look at how buoyant force is caused. Hopefully one of these will resonate with you. All right, I'll see you Wednesday.